on. Speakers, right. Yeah. Hi. Good morning or afternoon, everyone. I'm just gonna go get water. Then we can start the tutorial. So make yourselves comfortable. And I'll be right back. Okay. All right. Let's do this. Good afternoon, everybody. How are we today?
I'm good, Professor. How are you?
Oh, not bad. Can't complain. It's finally like sunny out past like 5 p.m. these days. So, definitely, definitely springtime's a happy time for me, I have to say. Matter
Yeah,
of
it's
fact,
lovely outside.
yeah. Matter of fact, I'm probably going to draw the curtains a bit because I'm getting so much glare. Yeah. So the today, chapter 37. It's a short one, but an important one because we're talking about the fact that back in post or I mean pre like 19th century, it was really hard to figure out what light was. If you think about the experiments that are famous, such as, well, the diffraction experiment, the photoelectric effect, or even the gravitational lensing, all of these experiments, you needed to have some kind of technology either like some advanced telescope, a sensitive telescope, or a way to sort of control and modulate your own light rays, a way to produce coherent light. So for you to see effects such as diffraction or the photoelectric effect, you really had to have um, the right technology for it. And, you couldn't have that even in like the 1600s. It really was sort of revelatory to be able to observe things such as diffraction or even the photoelectric effect, because you really had to go a long way in scientific development to get to the point where you could actually observe light like that. Because everything else, with sound, for example, if you were looking at interference for sound, it was easy to create coherent sound waves because you could build one of those tuning forks. Tuning forks have existed for centuries, right? Even waves on a string, right? All you needed was a string. But really, light took a long time to be understood. And even then, it took an even longer time for the observations to agree on what light was, because you had people saying it's a particle, some people saying it's a wave, and it took for Planck and so many other physicists to come in like about 100 years ago and basically rethink the way we thought of light, and in doing so came up with a whole new wave of physics called quantum mechanics. So anyways, point being is, you have to imagine that we are back in the like late 1700s, where there really isn't enough of an idea of what light is. We know we can't put it on a scale. We know it reflects off surfaces. We know, you have prisms, you can make rainbows through them. But the understanding of the world is that things are either made up of smaller things, particles, or they are waves, like ripples in a pond or sound. So if that's our understanding of the world back then light must be one of those two things. And when it came to people saying, okay, light might be a particle, you had people like Newton. But what Young did was actually provide very strong evidence for the first time that light had wave-like behavior. And this was a huge deal back then. So just wanted to provide context for why we have a whole chapter basically dedicated to Thomas Young. Anyway, so for the tutorial, I'm just gonna quickly go over some of the stuff I talked in the lecture. But like, the idea was that, well, so waves of all kinds can overlap, and depending on the components, but depending on what phase of the waves that are overlapping, they might overlap constructively or destructively or somewhere in between. And this is true for light. So if you get two light beams coming from two different slits respectively, you see that they project a fringe pattern on a screen. In the same way that if you're walking around two sound speakers emitting the same frequency, there's points along your path where they sound loud, and there's points where they sound quieter. So this is the same for light. There's points where light is brighter and points where light is darker. The cool thing is that with your experimental setup, just like Young did for your double slit diffraction box here, if you know how you set it up well, then you actually know how far away the slits are, the space between the barrier with the slits and the screen. You can actually then, from the geometry of the fringes, you can figure out the wavelength of your light based on where the fringes appear. So we also talked about how you can derive a general formula for the angular location of the bright fringes, and that's all the spots where the path length from between the rays of the two slits differs by a multiple of the wavelength, because that means that the second ray travels an extra distance equal to some number of wavelengths. So when it arrives at the same point, it'll be exactly in phase. Secondly, we call the central bright fringe in the screen the 0th maximum. And then any bright fringe besides that goes up in order number from 1 to 2 and so on. So it starts at 0 and goes to 1 on either side. Usually the positive side means a fringe on the left, or in this case, because it's the graph is kind of like on a vertical axis, will be the fringe up, and then -1 will be the fringe to the right or down. So there's also the dark fringes where the two slits, their lights arrive at a phase, and that means the path difference is a multiple of a half wavelength for them to be in that phase difference. So you can figure out the angular position of a dark fringe by specifying what the order is. So the M0 for dark fringe means the dark fringe immediately next to the central one. So there's a central bright fringe, and right next to it, right, is the 0th order dark fringe on either side. And then as you keep going outside of the center, you keep going in order. So like this. Oh wait, this got a little bit shifted in the transition. This should be a little. So basically, so the fringe pattern, right, is alternating minima and maxima. So the brightest spot is at the center, then there's the dark fringes at either side, then the bright fringe, dark fringe, bright fringe. The gap between the fringes is actually kind of follows like it's proportional to 1 over cos theta, but for the fringes that are like close to the center, so like the first like order, like from order 0 to order 5, all those fringes are basically spaced apart linearly, so you don't have to worry about the spacing of the fringes depending on the angle, because we're assuming that we're looking at a part of the screen that's close to the center, so you don't worry about the angle done, which makes the spacing between them just be linear. So where you can also find this, you can find where the light and dark fringes are located on the screen. Since you know the angle between the center of the screen and the fringe in question, it just takes some trigonometric algebra to figure out where the fringe is located. And to simplify things, if you're assuming that the angle theta is small enough, you can actually calculate the position of any fringe based on the wavelength of light, the space between the barrier and the screen, and the separation between the slits, that's D, and also what order fringe you're looking at, that's specified by M.
Sir?
Yes.
Like, what's considered like a small angle, or an angle where you could use this equation?
That's a good question. So, there's no like official, theorem that states what a small angle is, but it is agreed upon by rule of thumb that a small angle is any angle less than 10 degrees. So
anything like less than 10 degrees is like considered like a small angle?
Yeah, any angle less than 10 degrees is a small angle. So basically, the equations we derived are assuming that the distance from here to any point on the screen, this angle is 10 or less.
Okay, thank you.
So matter of fact, the textbook, a lot of the formulas in the textbooks, like the pendulum one and so many others, are defined for small angles. So every time the textbook says small angles, the assumption is always the angle is less than 10 degrees. And that lets you say that sine theta is approximately equal to theta. And that cos theta is approximately equal to 1, which makes sense, right? Because cos 0 is 1. So if theta is small enough, it's going to be close to that anyways. If it wasn't for the small angle approximation, then this formula will have a tan theta term. If you simplify it, it looks a lot like this formula, but now there's just a factor of 1 over cos theta. But for small angles, the cos theta is approximately equal to 1, so you're left with this formula here. Which, by the way, this tells you the position of a bright fringe. This tells you the position of a dark fringe, right? So you notice then that neighboring light and dark fringes are a factor of L lambda over D over 2 apart. Let me just write that down. So the distance between neighboring light and dark fringes is will be L lambda divided by 2D. And the distance between so two dark fringes next to each other, their distance is the L times lambda divided by D. Same with two neighboring light fringes. But for example, then the distance between light fringe of order 1 and light fringe of order 3, it would be 2L lambda divided by D, right? Because it's twice. Because the fringe of order 1 is a distance of L lambda over D from D1 of order 2. So then from order 3 to order 1, there would be twice that distance. Again, assuming small angle. It's kind of like the, you know, like in standing waves, how once you find like the harmonic frequency, each other resonant frequency was just like a multiple of that. It's kind of like that. It's a linear multiple when it comes to the distances between the fringes. So the fringes are not like a binary, like it's not like a here's light, here's shadow kind of thing. There's like a gradient of light to shadow, which you can't really see because of like camera and eye optics and really let you see the fine granularity between the fringes, but that's what's actually happened. Light in intensity goes up and down smoothly, and you can then find a formula for the intensity across the fringe pattern where the formula still depends on the angle, on the size between the slits, and the angle theta, which is the angle from the center to the point on the screen. This makes sense that it's a periodic function since the intensity goes up and down as you walk across the screen, since you're walking through light and dark fringes. And then if you have a small angle case, then the formula will simplify a bit nicely, and you can find the intensity at any point just knowing the configuration of your lab. So when Young did this, you know, he set up his diffraction like screen and everything himself. So he knew all the measurements. He then was able to locate, you know, the position of a particular fringe, and from that he could work out the wavelength of light should be for him to see a bright fringe where he did. So that's one way to calculate the wavelength of light. Obviously, the way it's done here, right, is with like the small angle approximation. You can still do it the proper way. That would just be dividing by a factor of cos theta, but the approximation is pretty good anyhow. And this is something you can actually do. If we had access to the lab at the college, we would be able to create our own diffraction patterns and like calculate the wavelength of like light bulb or source light ourselves, which is a pretty cool experiment if you ask me. Yeah, so also, look at this quick, I want to do some examples, but remember how if you send a wave on a rope towards a wall, it'll bounce back off. And then if you send it towards like a loose end, it also bounces back off. Well, the idea of that is that mechanical waves reflect. And we saw the light also reflects, but what we may not have thought about is the fact that there's a phase shift, there's a phase change when light reflects off a hard surface. So it's just how like the rope, when it hits a hard wall, it comes back upside down. Light does the same. It flips 180 degrees when it reflects off a hard surface. What's a hard surface? Just anything with a higher index of refraction. So light however, can also reflect through a thinner surface with a less index of refraction. This is analogous to when the wave on a string hit a free end, so it just kind of goes up and down and reflects back the same orientation. So if wave isn't like water and reflects off the air surface, it will not be a phase change. It'll reflect back into the water without a phase change. And the fact that the light can change phase as it reflects matters because light tends to reflect and refract as it moves through a surface. So it actually splits itself into many smaller light rays that are all reflecting and refracting. So some of them get reflected out of phase and some don't. So the light that gets reflected back overall is this combination of light rays, some in phase, some out of phase. And that means that the overall reflection of the incident light can be brighter or darker. And that's when you get these cool rainbow patterns from film, because some light kind of reflects off the top of the film, some light reflects off the bottom, and that leads to different parts looking more colorful on some colors of white light, while other parts look more intense in other colors, since there's interference happening throughout the film. So right, you see how like the incident light, some of it reflects off at the top, but then part of it goes on to reflect at the bottom and come back out. So basically one ray of light ends up breaking up into a bunch of smaller rays that get reflected out into the surface, and they end up combining in destructive or constructive interfering ways, leading to colorful patterns like the one you see here, or on soap bubbles, or like in birds. So the tricky thing though is that when interference happens for a thin film, you have to keep into account that one ray might be out of phase while the other one isn't, or they might both be out of phase. So that's going to have an effect on what the path length would be for you to see constructive or destructive interference. If two rays emerge from the film, one reflected off the surface, one reflected off the bottom, then one's going to be out of phase, which means that if their path difference is a half wavelength, then they'll actually be in phase again when they meet. They'll create a bright spot. But it's the other way then for destructive interference. If they're coming out of phase, then if the second ray travels a multiple of a full wavelength, then they're going to create a dark spot. The second ray travels an extra distance because it has to go through the film and back. And we're assuming that the horizontal distance is not that big, it's just a vertical one. So basically the second ray has to travel the thickness of the film twice. So that's the path difference. That extra distance the second ray travels is twice the thickness. But you also have to account for one more thing though for this interference, which is that the wavelength while it's in the film is modified by the index of refraction. So you have to account for that wavelength change while in the film to properly account for the path difference. So if you do that, then you can figure out what thickness is necessary for a film to create destructive or constructive interference.
Sir,
Yeah.
I'm like, I don't really like understand how incident ray 1 and 2 are out of phase, or are like not in phase.
So what's the difference between ray 1 and ray 2?
Like ray 1 is being reflected in air, and one's being reflected in the film.
Yeah, exactly. So ray 1, we're getting reflected in the air at the interface of the ray and the film, of the air and the film, I mean, is the same thing as a wave on a string hitting a wall. When that happens, the wave on the string gets reflected back upside down. When a wave reflects off a hard boundary, it gets reflected out of phase. So if you remember that animation of like the wave kind of looking like it's that looks like a peak, it hits a wall and then it comes back to the left looking like a trough. That's the same thing that happens with the beam of light when it hits the interface right here. Beam 1 comes back out upside down.
Wait, so
yeah.
So like ray 1 is 180 degrees out of phase with the incident, right?
Yeah.
Or
And
the ray
by the way,
2.
when you say 180 degrees out of phase, don't confuse that with the angle of reflection. By 180 degrees out of phase, we're talking about the wave's phase.
Yeah.
So yes, it's 180 degrees with respect to the incident ray.
Okay, because like I thought like it was like respect to ray 2. So like that's why I was confused.
It's also out of phase with ray 2.
Okay. How?
So that's a good question. So the wave, unless the wave is reflecting off a thick medium, like it does when it creates ray 1, the phase is not going to change. So part of the wave, part of the incident ray refracts into the film, and when it hits the backside of the film, this reflection does not cause a phase change because it's hitting off a surface of air below it. That's a less dense surface. That's like hitting a free end for a wave on string. So it gets reflected upwards without a phase change. So only when you hit a wall that's thicker than you will you bounce back out of phase. And that's what happens for the ray number 1 that hits the film and reflects off. But while the ray travels inside the film, when it hits the boundary here, this boundary is with air, which is less dense than the film. So when it reflects off and passes through, this reflection does not change the phase of the wave, because it's reflecting off a surface that has a smaller index of refraction. We're assuming that n, whatever it is bigger than 1.
Okay. I think I got it.
Okay, nice.
Thank you.
So in other words, you have one light beam here, incident, and then when it hits the interface, it's going to break up into 2. Ray number 1, and then the other half of the beam will pass into the film, and then it's going to break up into 2 again. One half of it's going to reflect back up. It's going to split into 2 again, and one of those halves is going to pass through back out, and that's ray number 2. So this reflection here changes the phase. But for the refracted ray right here, this refracted ray has the same phase as the incident ray. So the phase doesn't change from refraction. It can change from reflection, but not from refraction. So the refracted ray has the same phase as the incident ray. In this reflection, there's no phase change. This refraction, we know there's no phase change. Then ray number 2 must have the same phase as the incident one, which means that if ray number 2 is in phase with the incident one, but not ray number 1, then ray number 2 is out of phase with ray number 1. Now, what if instead at the bottom there wasn't more air, but there was actually an even thicker medium? So what's going to happen is ray number 1 is still reflecting off at this interface of like air and a thicker medium 1.45. That means it's going to reflect with the phase. Now over here at this reflection, it's reflecting off an even harder surface. If this were air, then this reflection here will not have a phase change. But now it's reflecting off a surface with an even bigger index of refraction. The film has 1.45, the surface has 3.5. So this reflection is also going to cause a phase change. So incident ray comes in, refracts, it's still in phase, and then at this reflection, it's now out of phase and comes back out of phase. And also at this point, right, it's splitting into 2. It's splitting into the refracted ray here, and it's splitting into reflected ray 1. Reflected ray 1, because it's being reflected at this interface where the index of refraction is bigger on the other side. Reflected ray number 1 is also out of phase. In other words, both beams are out of phase because they are both getting phase changes due to reflection. And because they're both out of phase relative to the incident ray, then they're both in phase with respect to each other. So if they're emerging out of phase, then you need to make sure that the path difference between them is a multiple of the wavelength to get constructive interference, or half a wavelength to get destructive interference. Okay. So I have some questions for you to try out. So maybe take like a minute or two to think about this one and write down the answer you think is best. So, an interference pattern, you might recall that an interference pattern is really just a superposition of two waves. But remember that when you create a superposition like a standing wave, the wavelength and the frequency are the same as those as the constituent waves. So the wavelength and frequency are the same everywhere on the screen. What changes, right, is the intensity of light, but the frequency or wavelength is the same. Right, remember the formula for like two waves superimposing, right? You had the amplitude, and then you had a term that was like cos phi over 2, but then you had like sine omega t, or like, kx minus omega t plus phi over 2, and that was telling you that the combined wave retains the same frequency and wavelength as the original two waves that made it up. So it's the same here. Okay, so you got a fringe pattern on the screen made through the diffraction experiment. And the question is, how do you increase the number of fringes per unit length? In other words, to have more fringes per unit length means that you're decreasing the spacing between the fringes. And by the way, the spacing between consecutive fringes, whether it's bright or dark, is equal to L lambda divided by D. So yeah, the question is asking, how can we make it so there's more fringes per unit length? Okay, so if we double the number of fringes per unit length, would that make the distance between the fringes bigger or smaller?
Smaller.
Yeah, because basically we have, let's say we can fit, in a unit length, we can maybe fit 3 bright fringes. So here's a little 1 meter of screen. But what we'd like to do is, maybe we'd like to, if we want to fit more fringes in the same length, so we have this much length to work with. space between the two little arrows. If we want to fit more fringes in, we are going to have to bring them closer together to make room for one more at least, right? We have to have like, so clearly the separation between the fringes has to go down. In other words, delta y is decreasing. Because delta y tells you the distance between any neighboring fringe. So if this is being smaller, then that means that delta y is inversely proportional to the slit separation. So if you double the distance between the slits, that's going to decrease delta y, which is what you want to fit more fringes. So this A is true. B is also true because if you decrease the wavelength, you decrease the delta y. C is also true because you would, even though you're increasing the wavelength, you're quadrupling the original distance. So what your new distance would be equal to delta y prime. L is the same, but now you have 2 lambda, which would increase the separation, but you have 4 times the distance. So that just basically becomes L lambda divided by 2D, which is smaller than the original separation. So the last thing is to increase the width of the slits, but that has nothing to do with the separation. There's no term for that. So the answer is D. Any of the above will help. So making the screen farther away increases the separation. Making the slits farther away from each other decreases the separation. And also longer waves will have a bigger separation between the slits. In fact, I'm gonna link you to an applet. I'm gonna link you to an applet that shows exactly what I'm talking about. Is the one? Yes. Nice. Okay. Let me find my thingy. So here's your coherent light source going through the 2 slits. And in the middle, we see what the diffraction pattern looks like. So if I click on this, I can make my slit width bigger. So right now it's as small as it can be. And as I click on it, it's going to increase. When I increase the slit width, that's going to bring the slits closer together. So see how they're coming in, and then resets, and then they're coming in. Also, I can modify the screen distance. If I bring the screen farther away, the slits are going to move away from each other. If I bring the screen in, they're going to move closer together. So away and closer, away, closer, away, closer. Lastly, I can change the color of my laser. If I make my laser green or blue, they are shorter than the red laser, so they're going to be closer together. So you see how the green laser has closer slits, so does the blue one. If we go back to red, the slits are farther apart. Again, it's a formula. The slit separation delta y is L lambda divided by D. So there you go. I'll post it in the chat. Okay, where did I put the presentation? Ah, here. Okay. Okay, so we are told we have two slits set up. There's separation installed. We shoot a green light through it. And we need to find the distance from the central bright region to the fifth bright band. And the screen is 1 meter away. Well, we don't know how to locate any fringe on the screen, so we can figure that out pretty easily, right? We can just we know some stuff. We know the length of the screen. The distance is 1 meter. We know that the separation of the slits is in millimeters. Is just typing stuff out. We even know the wavelength of light. That's nice. 540 nanometers. Be careful with nanometers. That's 10 to the negative 9 meters. Okay. What order is the fifth bright band on the screen? We need to specify the order of the fringe. What order is that?
5.
Yeah, I almost got tricked here because the first order you can possibly have is order 0. And that's like, so the central band, which is order 0, is technically the first band on the screen, which means that the fifth band is, right now I'm getting myself confused. Yeah, so the fifth band from the central band is order 5, but it's technically the sixth band if you count the central one. Anyways, but yeah, no, it just means, yeah, if you from the center, it's m equals 5. So you plug it all in, and it's 2.7 centimeters. So each band is only like half a centimeter away from each other. They have very small separations. It's a very small projection, which is why you can actually like measure this in a lab room, because the projection is fairly reasonably sized. It's still big enough that with like a good ruler you can get the fringe separation, right? Because even if you only have 1 meter of distance, the fringes are still like a few centimeters apart, that with a good ruler you can now measure out what y is, which is exactly what you do in a lab setting. Oh, this question. Okay, again, same experiment. The slit separation of the green light. How many bands of bright lines are there between the central maximum and the 12 centimeter position? So let's just try this one as a challenge. Remember that the separation from other end fringe to central fringe is y is equal to m l lambda lambda b. Well, that's the first time it crashes all semester. All right. And we're back. Okay, so how many fringes are there between the center and the 12 centimeter mark? In other words, what's like the highest order fringe that'll fit that falls below 12 centimeters from the center? Remember that the distance to the mth order fringe it's going to be equal to the order m times L times lambda divided by d. If you plug everything that you know, you get that then the distance will be m times 1.1 centimeters. So the 12th order fringe would be not in the area. That will be 12 point, what is it, like 12.12 centimeters? Gosh, 12. Anyhow, what you end up getting is that only the fringe of order 11 okay, actually you can't round up in this case. So what you calculate for the wait, what? Where did that go? If you calculate the separation, so it'll be 1 meter times 12 times 540 nanometers divided by 12 centimeters, you get about 4.5 microns. So wait, that's not right. Hang on. Okay, so the separation between two slits is the length, which is 1 meter, times the wavelength of light, 400 nanometers, divided by 12 centimeters. Look, I'm doing something wrong here. ML lambda. Oh, sorry, the slit separation. Look at the wrong place. The slit separation is 0.05 millimeters. Yeah, so 1.08 centimeters. So the 11th order fringe is at a distance of 11.88 centimeters, while the 12th order one is at a distance of 12.86. So y is equal to m is equal to 11 is equal to 11.88. And this one's less than the 12 centimeter mark, but this one's bigger than the 12 centimeter mark. So yeah, actually you can't round up here like I did. You have to keep it at 1.08 centimeters. So the 11 order fringe is right below the 12 centimeter position. So the 12th order fringe is not fit. In other words, there's only 11 fringes between the center and the 12 centimeter point. So the answer is C. By the way, this was a question on the 2018 midterm. It wasn't a multiple choice. You had to do it straight.
Sir,
Yeah.
I'm confused on what you did to y m equals to 12, and then like how you got that exactly.
Okay, so I derived, so first of all, I derived like the general, so I wanted to calculate the separation distance between the center of the screen and a fringe of any order. So does this formula make sense?
Yeah, but it wasn't asking for like how many bands there are.
Yep.
So like, I'm saying, wouldn't you solve for m?
Yeah, you can do that, and you would probably get like an M that's probably like what 11 point something, and then you'd run down to 11. You can, but the way I did it was that with this you can find the position of any band, and basically at some point there's going to be a band that's right above 12 centimeters. So any band below that one will fit inside. So I figured out that, okay, to find the distance to any band, I should multiply the band number by 1.08 centimeters. And band number 12 is above that line, but band number 11 is below that line, just below. So there must then, you can only go up to band 11 in the space given by the question, so there can only be 11 bands. That was how I did it.
Okay. But like if you like solved for m, and like would your y be 12, or what would be your y?
If you solve for m, if you set y to 12 and you solve for m, you would get that m is like 11.11. So that would
It still works then, right?
Well, so that formula will not have like a physical meaning, because this formula is specifically talking about the position of the bright fringes. But if you do that, if you still do that, if you solve for m, and you get an answer of 11.11, basically that's telling you that for there to be a bright fringe at y equals 12, the order of that fringe will have to be 11.11, which is not physically possible. But from that, you can then argue that, like, okay, if you need like an order of 11.11 to be at 12 centimeters, anything higher than that will be beyond it. So the first, like the closest physically possible order to 11.11 is 11. So the true last order that fits below 12 centimeters is M11, so there's 11 fringes. So you can still do it that way.
Thank you.
Sir,
Yeah.
how did we decide that the answer was going to be C?
Because do you agree that the 11th order fringe from the center is 11.98 centimeters away?
Yeah.
So if that's the 11th order fringe, which is 11.98 centimeters away from the center, from there to the center, there must be 10 other fringes.
Yes.
So if we have one fringe here and 10 fringes below it, we must have 11 fringes.
Okay, okay, never mind. I thought the ones represented the fringes.
Oh, okay.
Okay, thank you.
No worries. Actually, speaking of, we're gonna do some questions where we're actually gonna choose the fringes. Let me go to the next page. Where am I? Okay. So these are 5 different drawings. So these are 5 different patterns. 1, 2, 3, 4, 5. So you have to choose which one you think comes from a barrier with the smallest spacing between the slits. There's no ties, by the way. Only one of them has the smallest spacing. So, and also, let's say the white spaces in this case are actually the bright spots. So the bright spot, imagine it to be in the center. So one bright spot here, bright spot, another bright spot. Here's a bright spot, and so on. Here's a bright spot. Here's a bright spot. So yeah, one of these 5 has the smallest separation, the smallest slit separation. I'll give you a little bit to think about. Remember the applet I showed you. What happens when we change the separation? How did the pattern change? So we all had time to think about this. Remember what I said earlier, that the bigger the slit separation, the smaller the spacing between the maxima. In other words, the smaller the spacing between the slits, the smaller the E is, the bigger the distance between the maxima. So whichever one has the biggest maxima distance has the smallest slit spacing. In fact, it's 5. Because if you look at the distance between the slit, between the maxima, here it is. This is the biggest distance. Because if we look at 3 or we look at 1 or 2 or 4, it's 5 that has the biggest gap between right fringes than all of them. So the separation being inversely proportional means that it must be the smallest. Okay, so same question, but now we're looking at the picture that has the biggest spacing between the slits. So yeah, take a few seconds to think about that. Which one has the biggest spacing between slits? So the closer the fringes are together, the bigger the spacing between the slits. We saw this here, where as we increase the slit width, the fringes came closer together. So drawing 4 has the fringes which are closest together in any other drawing, so the answer is 4. Okay, so same 5 patterns, but now you have to pick the one. They all have the same slit separation, But you have to pick the one that are that have the, you have to pick the drawing that has the greatest wavelength. So I'll give you a few seconds to think about that.
Sir,
Yep.
so like when you increase like a distance between the slits, then you decrease the spacing between the maximas.
When you increase the distance between the slips, you decrease the distance between the maxima. Yes.
Okay. Thank you.
So this question is saying though, what happens? Each drawing here has the same distance between the slits. So which of these drawings corresponds to light with the greatest wavelength? The wavelength of light is proportional to the spacing between the slits. In other words, the longer the wave, the more spaced out the slits will be. The shorter the wave, the closer together they are. Let's look back at the drawing here. Red light has a longer wavelength than green or blue light. So based on what I said, that means that green light and blue light will have fringes closer together. And that's true, right? You see how red, the pattern's more spread out. And then for green, it's closer together and even closer for blue. In other words, the pattern with the longest wavelength will be the one with the most spread out fringes, which that's number 5. Because the fringes are pretty darn far apart from each other. Finally, you have to choose, assuming the spacing is the same, which of these patterns is caused by the light with the shortest wavelength. Give me a few seconds to think about that, but I think you might be getting the hang of it. Well, if the spacing is proportional to the wavelength, then the shorter the wavelength, the shorter the spacing. The one with the shorter spacing is pattern 4, so that's the answer. Okay. So on picture number 6, just talking about the intensity of light now, and along the screen, there's a point where the intensity is 3/4 of the maximum intensity. So the maximum intensity happens at the points of constructive interference, and then it drops from that to 0 as you go to a destructive interference point, and then increases back up to the max, and then up and down as you keep walking across the screen. But the question is, the distance, what's the distance y over the central maximum when the intensity is 3/4? So because the central maximum is a bright fringe, and you're looking for the point where the intensity is 75% of that, it's not too far. You can't be too far from the central maximum. So you should expect your answer not to be a huge distance. Anyways, even if we were kind of lost as to how we're going to find the distance y, note the fact that the question's mentioning intensity, and so far we only did have one formula talking about the intensity of the diffraction pattern. So we go right ahead and work out this formula here, and this is the small angle version of the formula, which unless told otherwise, you're allowed to use it. Assume the small angle applies. So, okay, if we know nothing else than the fact that we need to calculate y, we realize that, yeah, this function is proportional to the position on the screen. It makes sense, because as you walk along the screen, you are moving through the fringes, the intensity changes. Lovely, great. So let's solve for y. So at this point, even if you don't really know what's physically going on, you can just do algebra and figure out the unknown. So a few steps. Take the square root to get cos by itself. And if we keep going, right, if you write down everything you actually know everything except y. You know what pi is, you know what the slit separation is, it's all right here. You know L, we know the wavelength of the light. So over here, though, this might throw us off because we have a ratio of the intensity at the point and the max intensity. Well, we don't actually know what the intensity is exactly, or what the max intensity is, but have no fear, right? We can still always go back to the question and look for more information. There's one more fact we haven't taken advantage of, which is the fact that it tells us that the average intensity on the screen is 75% of the maximum. So here's the ratio of the average intensity to the maximum, and we're told it's 75% at point y. So that means that this ratio must be 75%. So we know then, we don't even have to know what I is, we know the ratio. So we can rewrite this as 3/4 of I max. And while we're at it, let's take the inverse cos function and let's do some quick algebra and solve for y. So at this point, you're basically on the home stretch. You plug into the calculator all the variables, and look, your separation is 48 micrometers. This is tiny, but it makes sense, right? Because if you look at the fringe pattern, the span of the bright band is like just a few centimeters, right? So the distance between this and just a little bit to the right or to the left is a very tiny distance. So it makes sense that your answer then is a small amount. It's always good to have an idea of what's physically happening in the question so that you can have like a conceptual way to double check your answer, right? Does it make physical sense that the distance to this point is 48 microns? Well, yeah, because diffraction patterns are usually no less than a few centimeters in width per fringe. So it makes sense that within a single fringe, the distance to the point where the intensity drops by just 25% is a small distance. If your answer had been 2 meters, you know you did something wrong in calculation. Okay. Let's do some thin film questions to wrap up. Nothing too hard. Try doing this one. I'll give you a minute or two to puzzle it out. I'm gonna get one more refill of water. Okay, so this is based on the fact that when light transfers into a new medium, what properties of the light change? What do we know changes over the light in a new medium?
The phase.
No. Actually, the phase of the waves remains the same when it goes to a new medium. When it reflects, it can change, but not when it transfers. Does the speed change?
Yes.
Yeah. In fact, the index of refraction is all about telling us how the speed changes in a new medium. Does the frequency change?
No.
Yeah, it doesn't. Because if it did, then you will have a that will not conserve energy. So yeah, speed changes, and so does wavelength. So you can actually figure out from the b is equal to lambda f that in the new medium, the speed of light decreases by a factor of n. So you can realize then that in the new medium, the wavelength in the new medium is just the lambda in air or a vacuum or whatever divided by n. So the wavelength is always shorter in a medium, in a dense medium compared to air. So whatever the answer is, it's going to be less than 500 nanometers. Because speed decreases, so much the wavelength. And in this case, the index of refraction is 1.4. So the new wavelength is 500 divided by 1.4. The answer is about 357 nanometers. Okay. Now we got a light wave, monochromatic. It's a soap bubble. And the question is, what is the change of phase of the light reflected from the surface? So this light, what's the phase change? So I'm gonna all do this all at once. Okay, so let's think about this. At the interface, what has a higher index of refraction? The air or the bubble?
Bubble.
Yeah, the bubble. So essentially, as far as the reflected ray goes, the part that reflects, the ray is kind of like hitting a hard wall, right? And when we hit a hard wall, we bounce back upside down. So the reflected ray is going to be out of phase. So that'll be the answer, 180 degrees. Okay. So now the question is, how thick is the bubble that destructive interference occurs in the reflected light? Maybe I'll give you a little bit to think about that one. Maybe so if you can track it. I'm gonna go right ahead and then maybe put some labels next to the rays. One, two. Okay, is ray number 1 in phase with the incident ray?
No.
Nope, because it reflects at a hard boundary, so it reflects off out of phase. Is ray number 2 in phase with the incident ray?
Yes.
That's right, because look where it comes from. It reflects at a soft boundary from water, from soap to air. So when it bounces up like this, it remains in phase. When it refracts out back to air, refraction does nothing, it's still in phase. So this is in phase with this one is out of phase. So these two are out of phase with each other. If they're out of phase with each other, then to create destructive interference, that's going to happen as long as their path length is a multiple of the wavelength, because they start off out of phase. So we know that the path length must be a multiple of the wavelength. The path length is always twice the thickness of the bubble, so 2t is equal to lambda times some integer. And even though the question is not clear, it's actually asking for the, because like the path length can be anything, because you can keep covering a distance as a multiple of lambda, but the thickest possible path length is, sorry, the thinnest, the thinnest possible value for t is for a path length of just lambda. So we could also like just a general formula for the thickness would be lambda n divided by 2. So the thickness of the bubble can be anything as long as it's a multiple of lambda divided by 2, right? But for the thinnest bubble, right? Because we're assuming that it's made of soap, so it's of course going to be as thin as it can be. Is equal to 1. And usually the textbook is going to be like, yeah, what's the thinnest bubble that can be made? Blah blah blah. It'll specify. T is equal to lambda divided by 2. So also it's worth pointing out that when it travels in the bubble, the wavelength changes. So lambda here is actually not the same lambda that you have in air. Lambda decreases in the bubble. So also I think now they use m for the path multiplier. They use m because they keep n for the index of refraction. So here. We already found, by the way, what lambda prime is. It's 375 nanometers. So if you go ahead and plug that in, you get an answer of, by the way, since the only like metric measurement in the equation is 500 nanometers for lambda, in my calculator, I would just keep it as 500 because then I would know that my answer is in nanometers. I don't have to like, get lost doing near the multipliers since there's just one number in nanometers, the answer will be nanometers, whatever. So the thickness ends up coming down to 1.78 millimeters, which makes sense because it's a soap bubble. Okay, does anyone have any questions about the chapter so far? So this is really as much math as there is for the chapter. The last two things, I was just talking about the interferometer and the Newton bubbles, which is just a way to check the purity of a lens. But that's, I can tell you right away, I'm not going to ask you about that on the midterm. That's just kind of like a cool application because interference the textbook talks about. Yeah, look, I feel like we always go up till like the very last minute, so we can end up 3 minutes early today. Have an early weekend, I guess. So yeah, that's all for now. We'll see you next Wednesday, and then Friday we'll do the pendulum lab. Keep your eyes open for the lab manual coming a few days before then. And otherwise, if there are no further questions, I wish you all a good weekend and enjoy the extra sunlight.
Sure. Hello.
Thank you, sir. Have a good day.
No worries. You too. Have a good one.
Thank you.
You're very welcome.
So will you be uploading the tutorial that we had on March 17th?
Yes. Did I uploaded that yesterday, didn't I? At least I thought I did. Actually, I had a student email me about that yesterday, so in response, I put it up. Let me check the YouTube right now if it's there. If not, I'll do it right away. No worries.
Sir.
But I think it should be up. Oh man. Or unless I had to re-record some stuff today, so maybe. Oh yeah. There's tutorial number 2 is up here. That's last week's tutorial, no? Yeah. Okay. Yeah, it's on YouTube. Look for chapter 36 tutorial number 2. Should be there. Should be in the channel. Well, I should put a link to it. Easier said. Easier said. Easier done. Yeah.
Hello.
Okay. Someone else have a question?
Yes, sir. I have a question.
All right, let's hear it.
The lab on Friday, is it in person?
No.
Okay, and also for the midterm,
Well,
is the
Sorry?
and for the midterm is the material only covering up to chapters 37.4?
37.4 is the thin film interference.
Wait, let me